I think we can start now. Today we invited Dr. Sadayuki Yoshitomi, and his talk is going to be about the recent updates on automated spice model development ecosystem for from an industry perspective. Sadayuki-san has a lot of experience in modeling, and he's currently working for Megachip Corporation, where he works as a chief specialist of optical communication IC products and technical marketing for 6G technologies. He has a lot of experience with BiCMOS and 3D NAND flash memory products as a team manager at I think Toshiba. I'll let you present your slides, Sadayuki-san, and then we can discuss more about the modeling part.
Yeah, thank you, Mehdi, for the kind introduction. So Mehdi, may I start now?
Yeah, go ahead.
Okay, thank you very much. So welcome to my session. So I will be talking about spice model development ecosystem. The content of my presentation is contained from my ex work, which I worked in Kioxia and Toshiba. Okay. So, and based on that, my ex work experience, I added some kind of new topics, and I also cover some test structure information for the calculation of parasitic extraction tools in this presentation slide. Okay, I start from the motivation of why I built up the PDK model spice modeling ecosystem in my ex work. So this illustration shows a designer's mindset, how to set a design target in a IC design process. So as shown in these illustrations, achieving the target specification is this part. At the worst corner condition is a requirement for the tape out. And this silicon performance is a real performance after in the production phase. So, and between this blue line and red line, so we call it's a design margin. And this is a designer's pain, honestly saying. And if we have a look at what kind of contents are included in margin, so margin included inaccuracy. Most of the margin include inaccuracy of the prediction, such as a yield prediction, and reliability prediction, and also spice modeling prediction inaccuracies. And if we move on the development by using the use of advanced CMOS technology node, like in the right-hand figure. And this if we launch on the new development project by using the advanced technology node, and usually the higher speed performance is required in the new generation chip design. So in that case, the designers will face much more margin for the previous models. And if we continue this kind of usual typical approach to have more margin between generation and generation, so in the end, it may not even be possible to achieve the target specifications at the schematic design stage. This is a nightmare of the circuit designer in the future. And maybe this nightmare is already started, I can say. And I've been working on this margin reduction for many years. And there I found the gap between our PDK team, which I'm leading, and the design team with respect to the accuracy of the models. As you know, designers are looking at the mass production stage But here, this is a designer's perspective. But our PDK team is looking at the silicon at a given snapshot, like here. We produce a model at on the of the silicon wafer at a given time slot, and we add the long-term property prediction into the SPICE model library at the final stage of the PDK development. But after the compression, we usually don't verify the accuracy during the mass production phase. We PDK team don't take care about what's going on in the production phase. This is our develop scheme issue, scheme problems to develop and brush up the PDK. Therefore, if the product characteristics deviate from the prediction by the circuit design teams, designers always claim PDK team that saying that the inaccuracy SPICE model caused this deviation. So therefore, to bridge the gap between our PDK team and manufacturer's team and design team, so we decided to set out to build a system for frequent update of the SPICE models and the system to link the design and manufacturing. This is a motivation to develop the PDK ecosystem. And from now on, we'll explain the portfolio of a PDK ecosystem. So this slide shows a whole picture of PDK SPICE model development ecosystem, which we have built in my previous work. So this system enables continuous monitoring of silicon characteristics as they change from early development stage to mass production stage. So as you know, in the beginning of the development stage, the silicon characteristic changes from time to time from lot to lot. And at the end of the mass production state, this is a stage that silicon performance stabilizes. But in a PDK development scheme, so we usually receive the wafers in the process ramp-up stage and create a model. So this is one of the cause of communication gap between circuit design team and our PDK team. So to reduce this communication gap, so in this slide, we four key technologies are summarized, shown. First key issue is to track as the silicon performance as a form of SPICE models as frequently as possible. This is fast tracking system represents this iteration cycle in this part, in this figure. And in addition to the conventional DC characteristics, as is always run by the usual ASIC foundry, so in this system can also monitor the high frequency characteristics associated with S parameters, as shown in this kind of GSD test structure in this picture. And this is a second key issue of the layout of test structure for the dedicated to S parameter measurement. And also, the third important key is high volume measurement. And in addition, I'd like to say that the Fablink compact model, which will be explained in my presentation later, which provides a Six Sigma design environment that can be used to establish a bridge of factory and design team. These four key issues are important component of the SPICE modeling ecosystem. So we will now discuss four major technologies shown in this figure in the subsequent slide. First, this slide shows the automated tools and information flow used in the work to perform the SPICE parameter extraction. So this is this block stand for the extraction steps, and blue line stands for the name of the commercial EDA tools, which I can say the commercial based EDA tools. But we need a customization in order to fit our workflow. So we usually, in order to fit our this line of tool bunches of tools into our workflow, we use the Python code to customize an environment that fit the data transformation between two EDA tools and the computational works we need to do.
So, Sadayuki, I have a question. By the way, Jacob, can you mute yourself?
Sorry.
Yeah. Okay. Well, I'm wondering. So you're doing auto measurement there. So it sounds like it's fully automated. But what is the step between modeling and auto measurement?
Okay.
So what is that step doing exactly? Sorry, I missed that part.
Oh, okay. So this spice model automation flow starts from the auto measurement scheme. This represents this here, which say in this slide, I wrote down as auto measurement scheme. This is this measurement scheme is already automated. I can explain you in my following slide. And we collect the data set by the auto measurement setup. And we by using this data set, we run the measurement QA program to automatically QA the measurement data. What kind of QA criteria we used in the measurement QA procedure is that if we find the data consistency with the same bias condition, with the same bias condition, with different kind of set of measurement. This is also automatically done by automation flow. But the modeling scheme, and if we have a look at the modeling scheme, the golden die selection is automated in our workflow. But model parameter extraction, such as core model and macro model, we have some kind of little bit iteration process.
I see. Right. And I'm guessing the structures where you're doing that are known and understood, right? Like,
yeah.
Do you have that list of structures you're using?
Yes. In my slide, yes.
Okay, great.
Yeah.
Thank you.
Oh, my pleasure. This is exactly what you want here.
Yeah, I should be patient.
Okay. So most of the audience in this working group meeting are familiar to the DC test structure, low frequency characterization. So in my presentation, I addressed the RF test structure needed that we used for the spice modeling ecosystem. But this is an additional part of the test structure. I have to mention it. So this is an example of designing of averaging pattern to register the S parameter in big data set. So based on the usual GSG pattern, this is a usual GSG pattern. The approximation size is like 300 micrometers in north to south and east to west size. This is a usual conventional GSG test pattern, but this conventional GSG test pattern is not good at fitting the scribe line area. So we designed this kind of scribe line type GSG pattern in order to fit the scribe line area. But to design the scribe line type GSG pattern, there is a lot of design issues. In order to have this performance compatibility with conventional GSG patterns, So there is a difficulties in three parts to design the scribe line type GSG. The first one is most of the difficult part to realize scribe line GSG pattern is a location of signal path. So signal path is here and here. And to establish a routing line from this signal path to the device edge, so we have to route the very long track lane from here to the edge of the device. And furthermore, we have to, here, this is ground line is very close to the signal line. So we have to take account the distance from ground. And furthermore, because this north to south distance is really very tiny, so we have to optimize the width of signal line in order to reduce the parasitic series resistance impedances. But this is not an easy task. So to optimize this kind of layout, so we used the electromagnetic simulations after to optimize this pattern in order to have as much compatibility result as conventional GSG patterns. So this is a result between conventional GSG test structure and this scribe line type GSG test structure. Still, there are discrepancy inconsistency after 20 gigahertz region. So there is a room to improve this quality of test patterns in order for the further. This is a further investigation topic. But for to some extent, so we succeeded to implement this scribe line type GSG pattern in our mass production control. And this is just so this slide shows the de-embedding procedure, how that was used when performing on-wafer measurement up to 120 gigahertz. This idea to de-embedding is to create a pattern that decomposes each part of the GSG test structure. Here, this test structure to obtain the S parameter for each part of GSG test structure represented by the inside the square part of the rectangular part with different color of this GSG test structure. So how we do de-embed by using 4 test structure is, so we obtain the A matrix element of these 4 test structure patterns, and we create the A matrices such as represented by this A1 or 1/2 part, 1/2 through A, and 1/2 line, and the test structure, whole test structure A matrix is represented by ADUT. So to obtain each matrices after the measurement, we multiply the inverse matrices of to the ADUT in order to obtain the A matrices of A MOSFET. This is the A parameter what we want, and from the A parameter we transform the A to S matrices or either A to Y matrices that we want to model, we want to use for the modeling. This feature of this four patterns has a good feature to fit our development flow, because by using this test structure, we don't consume silicon area so much. as compared to the typical TRL de-emitting pattern, which requires a lot of silicon area to establish the de-emitting pattern on chip. Okay. And from here, it's a bit of a beaten path. But here is an example of the GSG evaluation pattern design needed to calibrate the parasitic extraction engine, such as the EM simulator and the PEX. So creating the environment for parasitic extraction requires comparing the actual test pattern measurement of the electric permittivity and wear resistance and interconnected layer resistance and fringe capacitances. These four matrices are target to calibrate the EM electromagnetic, either EM simulation engine or PEX extraction engine. And this table lists the prototype patterns used as to develop the EM EM setup or PEX setup. The pattern for evaluating the pattern for evaluating relative permittivity. This is stand for here in this table. It is desirable to place a guard ring here to accurately estimate the substrate resistance. So usually this size of the test structure is something like 300 microns and 300 microns big, and to this part represent the square shape of metal wire line. Okay. And in order to accurately estimate the substrate resistance, so it's better to place a guard ring in order to have a how to call it, termination of electrical magnetic waves to the guard ring. Otherwise, we will not have a correct estimation of wear resistance and wear resistances. And here you see the four equations in this table. These equations that transforms to each parasitic parameter extraction, such as COX, it's a coupling capacitance to the substrate. This is represented in this figure also. And substrate impedances, G sub is a parallel combination of R sub and C sub. These parasitic impedances in the silicon substrate. So these parameters, four parasitic parameters, can be calculated based on this test structure by using the Y parameter matrix manipulations. Okay. And if we have a look at the fringe capacitance extraction, I used for two kind of MOM cap test structure to calibrate the parasitic extraction engine. So if we have a look at the fringe capacitance extraction pattern, so you can see the close-up of the pattern here. Two kind of pattern is illustrated in this table. So for fringe capacitance between metals, to extract the fringe capacitances between metals, so I have to mention that this blue line, which I can say that the first metal track line, let's keep the line and the space of this first metal the same in two cases and change the width of second metal. So if we change, so there is to to compare the capacitances between these two set of test structures, we can see the differences of fringing capacitances between first metal and this metal in red. So to verify the quantitative numbers of fringe capacitances, I'd like to propose the number of combination of metal layers and the number of widths of lower metal, which I say in this table are red line, red metals. At least two conditions are good to obtain the rough numbers, and three conditions, three different widths is very good to have a more accurate extraction of the fringe capacitances. It depends on the requirement, how many numbers are. It's a discussion of the silicon area cost and the number of variations. And it's also good to have a different lengths patterns with several variations, minimum two different kind of length variations by using based on this pattern is preferable. And the third one is fringe capacitance, such as via capacitance extraction. The same the configuration is the same using the MOM cap structures. And the only difference is that two metal layers are stuck in a MOM cap structure. And we prepare the one set of MOM cap structures with via connected and without via connected. So to subtract the capacitances between two variations, so we can obtain the via to via capacitances at the end of the day. So we have to take in account, because this via to via capacitance is really small number, so we have to take in account the number of fingers at the beginning of the design test structure design stage. But but from my experiences, I think the finger numbers such as 100 is enough to extract the via to via capacitances and with a reasonable accuracy. If you have any questions about these test structures, I'm ready to answer. So please interrupt me anytime. Okay. So now I move on the mass measurement hardware. I'm talking about hardware advancement. So this is a list of measurement instruments I used in my previous work. And I have to say that the performance of the network analyzer of the recent model has been improved remarkably. And the experimental measurement time is much faster than the old model. And furthermore, once I succeeded calibration time is less. Okay.
Sorry, Sadayuki-san. There's a question from Marcus. He's asking about the parasitic extraction structures. Are they documented somewhere in a book, or are those used from internally in your company?
Oh, it's not documented. It's internally in my company. But it's, yeah. But you already have this screen now.
Sure.
Okay. Okay, I go back to the list of measurement instruments. So I have to say that the network analyzer's advancement is really very remarkable. And once I succeeded calibrations, this kind of most of the up-to-date network analyzers is really stable for between 2 and 3 days without any calibration. And this helps us greatly extending the time for continuous measurement work. And also, The performance of semi-auto prober has also improved. In particular, improved image recognition technology has drastically improved. Thus, the accuracy of RF probe alignment in the X, Y, and Z planes enables a stable measurement of the GSD scribe pattern shown already on the page 8 at all points in 300 micrometer warehouse. So what I mentioned is this one, I think, this pattern. Here is a result of an automated S parameter measurement of a 300 millimeter warehouse using this most up-to-date system. So again, this is a test pattern which I shown in a previous slide. So to obtain the one-half pad aberration pattern, which already I shown in page 9, it was used for the evaluation. This is to probe this pattern is really challenging, even manually. But this is a statistical deviation of S parameter, which was obtained to 100 chips on the 300 millimeter die, and the frequency, measurement frequency was swept from 1 gigahertz to 60 gigahertz. And if we have a look at the standard deviation of S11, the value number is 0.13 dB. It's quite a good, it's a really good numbers by using this kind of challenging test pattern for the auto measurement for 60 gigahertz. And this is a rough estimation of time duration needed for this set of this measurement. It's less. I wrote down it's less than 10 minutes, but it's only a few minutes to complete this measurement. And furthermore, this is a new additional information. If we apply this new system for MOSFET measurement, including IDBG, two kinds of IDBG, linear region, saturation region, and IDBD, and S parameter measurement, all kinds of 4 set of measurement. We need only 4 minutes per device. This is rough. Thanks to the advancement of network analyzer, so S parameter measurement takes only a few minutes to complete this kind of measurement set of measurement. So this includes the 49 bias conditions and 110 frequency point. This is quite effective to collect as many numbers of transistor data on the whole warehouse, 300 millimeter warehouse as possible. It's pretty good. Okay, so from now.
You might have mentioned this, but how do you arrange all the pads, like all the small bare pads? Do you have to follow some format?
Yes, we have a concrete format, and we have actually say 4 or 5 kind of probe configuration format.
So what is the distance between 2 of the blue bare pads?
This one. This one is typically, I think, 200 microns here.
Oh, that's pretty large.
Here. Yeah, pretty large, yes.
Okay.
And I have to add some other information here. I wrote down here. Conventional GSG, we can change between 100 micron to 200 micron if we follow this configuration, usual configurations. And if we follow this scribe line type GSG, we have to pay attention to the how to call it shape of the GSG probe. So there is an interference because GSG test probe has a insulating layer like this, like here and here. And if we reduce this number down to 160 microns, it is not possible to place a GSD probe in this east to west directions. So this is from my experience, to keep 160 micron is a safe numbers to
Yeah. So the
to
work
have.
we did with NIST is around 40 micron from edge to edge. So I'm wondering why is it so large in this case here? Is it because of the probe card or from some physical considerations?
Here you mean?
Yes.
Generally speaking, yeah, you are right. You can we can reduce this size, and only to be honest, I wrote down the numbers of the, for example, this pitch.
Mm-hmm.
So we can reduce a now pitch size down to 50 microns, and the pad size also can reduce to 40 microns.
Sure.
So yeah.
So, I mean, I guess the question, you were talking about density, right? And I was wondering, why wouldn't you just squeeze in the pads distance, like the pitch between each pad and the pitch, the pad size, right? Like then you can get much more density. This is why
Yeah.
I was asking.
I see. But so if we increase the density of a part, there is one major drawbacks in order to characterize the very high frequency S parameters. So we have
Got it.
yeah, there is a interaction between this part, and if you have a part of the neighbors here, which is very close to this transistor we want to measure, so there is an interaction of a field coupling is generated from the probe. Even though if you try to measure this transistor, but there's a leakage of electromagnetic waves to the patterns which are connected to the neighbors.
Sure.
And this makes measurement accuracy a little bit untrustable.
I see.
Yeah. So we have to design this kind of GSD test structure for 300 gigahertz modeling characterizations. I joined the IEEE P2822 sub-working group to standardize the RF test structure for terahertz silicon measurement. So I think in a few months, so you'll get this standardized document at hand. Just for your information.
Yep. Thank you.
Okay. Let's go back to the... Okay, now let's move on the Fablink compact model. Okay. So I explained to the development of hardware and recent update of test structure for RF characterization in production, as a process monitors. So this part, I'd like to explain the compact model, which established a Six Sigma design called working platform between design team and the factory team and the PDK team. So in order to take the full advantage of the treasure of big data lying dormant in the factory and provide a Six Sigma design environment, our PDK is in my X work in Toshiba, we felt that the three enhancements shown in this table were necessary. So designers use design of experiment to identify the primary component. This is an image of DOE, design of experiment simulation result in this table. that are significant to the target index. And if we run the DOE analysis, this helps the designer to communicate the result directly to the device team. This is the concept of how of the fab-linked model which we want to develop in our development scheme in our product. So in this sense, what is asked to develop for the PDK team is to develop the model which should have the variables as such as a device geometry, of course, and the items that are stored in the big data, which are stored in the factory database. And we thought that once this ideal environment is created, design team will run spice simulation, which will reveal the key fabrication processes, such as in this figure, which I wrote the raw GC, CGD, RWare, such as a kind of image of DOE result as a palette chart. And if we find this kind of, if we find a result by way of a palette chart, we can get the information of the process variables directly from the spice simulations and tell the processing team which kind of factor stored in the big database should be much more finer control in the fabrication process. This kind of iteration to create this kind of iteration loop between three teams in a design scheme, it is a good scheme. We thought it's a good ideally conditions to develop our product in a faster time period and with higher yield. This is a concept of the feature of fab-linked compact model. So how we do that, it's a problem. Okay. So here's just a summary of the SPICE model of MOSFET, validated to 110 gigahertz. So this main part is vision for model, which is already familiar to everybody. And this is based on that, we usually create the macro model configuration, which can have a good fit with very high frequency data. Okay. And this macro model is good to predict S parameter from DC to 110 gigahertz with mulch bias condition. And also the geometry dependence of parasitic element at 60 gigahertz is very good, accurately represented on the right-hand side, these figures. And based on this, model frame is very good, and which is valid to 110 gigahertz. So, and here, I'd like to explain the big data in the ecosystem. So big data in the ecosystem area which we developed consists of two types of data set. First one is widely used, widely called as an inline data here. And second is also additional data set containing S parameter data, which I already explained in my presentation. The use of scribeline GSG pattern provides us with many variable information that helps us to explore the reality of statistical variation of the transistors, because this pattern is almost the same as the same size of the transistors in the circuit, which means that to collect information from this test structure, we can explore the source of variation of the real structure, real size of transistor, and which gives a very, very good information, better information rather than the inline data. To combine this two data set, we created the whole kind of data set who addresses whole kind of, or every kind of source of variation. And this figure shows how B-SIM4 parameters can be mapped to the items stored in the big data set. Some parameters such as TOX and RDSW, source drain schist resistance, and XJ junction depths that represent the physical structure of MOSFET can be directly mapped to the median and sigma of the big data set. It's no problem. On the other hand, there are some big data items that are correlated with many B-SIM4 model parameters, such as channel doping concentrations, represented by NDEP in the B-SIM model parameters. So in the next page, we will show how to incorporate this kind of parameters, which have a lot of more correlations with model parameters by using the NDEP case. Actually, NDEP has a lot of correlations with many B-SIM4 model parameters, and such as mobility and junction capacitances. So I will explain how we treat this kind of inline data parameters into SPICE models. So we want to, let's focus on the mobility, how to map NDEP inline data for mobility functions. We just want to know how mobility changes by changing the NDEP. So we created the empirical equations to trace the well-known relationship which is written in the semiconductor physics handbook. So to follow this trend, so we created empirical formula. This explains it here. And then the fluctuation of mobility is determined as a ratio of this function FU represented by FUE, NDEP, bracket NDEP. And the NDEP is numbers which fluctuated, and NDEP 0 is a nominal value. So we replace the each model parameter stored in B-SIM model card as to implement this kind of term of fluctuations like this. And for the CJ fluctuation, junction capacitance fluctuations, we use the same kind of approach. And CJ's fluctuation implementation example is shown here, like that. And this shows the actual integration example into PDK, where changes in multiple model parameters expressed. This is a B-SIM model parameters, part of the B-SIM model parameters here, written here. And this function form is represented by the process parameters those belong to the big data set. And in order to run the Monte Carlo simulations, we only need to the set of numbers of nominal value represented here, and sigma in the statistical module, which also so we can refer the big data set directly. The model we created was compared with a distribution of alpha characteristics of MOSFET like here. Yes, it's pretty much good, okay. And the palette chart, this is a use case of the designer's point of view. Please have a look at the palette chart. This palette chart shows a result of design of experiment simulation result by using the big data and this process process-oriented compact model. So from this chart, we can understand the channel concentration NDEP is the most vital variable. And it is also worth noting that the second vital parameter is different in two design targets, such as voltage gain at 1 giga and bias current. Overlap capacitance is vital for S21, 1 gigahertz gain, and bias current for TOX is vital for the bias current. Like this, we can realize this strengthen the end depth control helps to enhance the robustness of this amplifier's performance. At the same time, device team can understand the end depth controls important and go back to the factory and optimize the process. This is exactly a Six Sigma co-working environment so that both process and design and factory team can collaborate together in order to obtain a higher production yield. So finally, I'd like to comment on the future technologies. I think that there's a lot of room for DX technology to contribute the ecosystem to the semiconductor fabrications. Currently, there are no full auto testers like this. No full auto testers exist in the world for the S parameter, high frequency S parameter measurement. So we believe that to accomplish the hardware development and fully automated model parameter extractions, scheme will realize the advanced design for yield technology. Okay, this is a summary of my talk. And I have some information of the how to my reach out. So I had a meeting with MPI Corporation persons, and they told me that. So I explained the MPI Corporation team in Japan, and the Japan team contacted the MPI team in Germany. And this Mr. Stoan Kanef is a contact person of the MPI team Germany. And he said that he will contact semi-model team soon. That's why I asked Marcus to keep an eye on the incoming email from Mr. Stoan Kanef. And in order to access the available measurement equipment in Japanese domain, I contacted the several measurement vendors located in Japan. And from the beginning, they didn't say yes, but they said, okay, let's have a discussion, brainstorming session. So the brainstorming session is scheduled around the middle of May. And I did a reach out of the Japanese academia, and Professor Ko Joguchi at Shinshu University, he is in favor of the offer the workforce by some means. And he is ready to talk how to cooperate, how to join our team, and he's ready to talk how to proceed, how to join in this communication group. And he promised to send us a list of available measurement instrument in his laboratory soon. Okay, thank you for your patience. And that's the end of my talk. If you have any questions, I'm sorry I spent most of the for 1 hour. Sorry.
Thanks so much, Sadayuki-san. This is great. I think it was very insightful, and it's great to have a technical, detailed perspective from experts from the industry. So I'm wondering, is the professor from Nagano?
Yeah, it's Joguchi, Professor Ko Joguchi.
Yeah, please feel free to invite him and send an email to Rob, and he can add him. And is there any questions from the audience?
That was an excellent talk. Thank you.
Thank you very much.
Also, it's at 2 a.m. in Japan, so.
And this there is an interesting web pointer that MPI website. They open to some kind of program into the GitHub.
So I do have a question for you, Sadayuki-san. So yeah. I think you reviewed the tape out you did in MPW5. So I think it would be great if you can, during your brainstorming session, to add more structures or, improve some of the things we did with NIST.
Yeah. My pleasure. So since this my expertise is not helpful to proceed my current career because I belong to design team, but I have a lot of experience of PDK development, so I'm very glad to help you join this brainstorming.
All right. Any other questions or comments? But in general, I think these are really positive comments, Sadayuki, on a chat. So
yeah, of course. You can everybody can ask me any kind of related any kind of questions related to the PDK development. I'm very glad to answer.
sounds good. So I think we are about the hour here, Sadayuki-san. So thanks so much for the presentation and staying late in Japan. So
my pleasure.
Yeah. All right. Thanks everyone for attending. And next week, in 2 weeks, we'll probably have Benjamin from Germany to give us a presentation about.
Sorry, I occupy a whole time slot.
It's all right.
Sorry.
I think it was worth it. Thanks so much.
Okay, my pleasure. See you soon.
Bye-bye.
Thank you very much. See you. Bye.
See you.